We now discuss one of the most important topics of assembly language and microprocessors, which is basically the addressing mode, right? And the addressing mode is important because every assembly language instruction deals with the addressing mode. Or in other words, we say that every assembly language instruction that we execute has got an addressing mode. So without the proper knowledge of the addressing mode, we cannot do effective assembly language programming. So now basically what addressing mode really means. Addressing mode means the way in which operand is specified in an assembly language instruction, right? So basically when we talk about an assembly language instruction, we have got basically an opcode, pardon my writing, followed by operands. So for example, if we have move AX comma BX, move is the opcode and AX and BX are the operands of this instruction. So basically, however we specify the operand or data of the instruction, this is termed as an addressing mode. For example, in this example instruction, we are specifying that the source as well as destination of the data is an internal register. Source is BX and destination is AX. So since both of these operands are registers, we can say that this is an example of register addressing mode, because the operands are specified in the registers BX and AX. So as it says, AX and BX are operands specified both in internal registers, so it is called register addressing mode. So one of the fastest and most efficient addressing mode is basically the register addressing mode. So why is addressing mode important? Because it tells processor how to get the operands. Now when the processor is trying to execute the instruction, the processor knows that both the operands are in internal register. The source operand is in BX and the destination operand is in AX. So we tell the processor how to get the operand by specifying an addressing mode. And this is called as the data addressing mode, because we tell the processor how to get to the data, because BX and AX would be the data that would be used in this instruction. There are different addressing modes, right? There are program memory addressing modes, stack addressing modes, and so on and so forth. So now let's look at what are the types of data addressing modes. The first that we already discussed is basically the register addressing mode, because the source and destination are both processor internal registers. So there were two operands in this instruction and both operands are internal register of the processor, hence the term register addressing mode. The next one is the immediate addressing mode. And immediate addressing mode transfers an 8-bit or 16-bit immediate value into an 8-bit or 16-bit register. Okay. Remember how we discussed how the program is stored in memory? The first location stores the opcode. For example, if this is offset 0000, it would hold the opcode BA. BA is the hexadecimal equivalent of an assembly language instruction. Basically, assembler creates this BA. So now we have operand 1 which is 20 and we have operand 2 which is 10. So basically, following the little endian format, this is the low byte and this is the high byte. Low byte is stored at address 0001 and high byte is stored at address 0002 hex. Okay. So basically this is an equivalent of the second instruction as it is shown. Move DX, 1020. Now what does it mean? That whenever the instruction would be fetched, first the opcode byte would be fetched, the opcode byte would be decoded, followed by the operand 1 and the operand 2. Now what basically happens with immediate addressing mode is that the operand, which is 1020 hex in this case, is treated by the microprocessor to be the data itself. So whenever the processor has fetched the full instruction, the processor also fetch the data of the instruction. So the processor does not need to make another memory reference in order to get to the data. So this is called immediate addressing mode, because the immediate data is included as part of the instruction. So this is one of the very efficient addressing modes, because the processor gets the data along with the instruction, because data is stored along with the instruction. So the processor does not need to make an additional memory reference in order to get to the data. Some examples of register address instructions, right? What would be the main idea about this instruction? Both the operands would be internal registers of the processor, as can be seen over here, right? Now this instruction is not allowed, right? Because this is also a segment register and this is also a segment register. So both registers cannot be segment registers in register addressing mode. Similarly, this is illegal. Why is this illegal? Because one operand is 16 bits and the other is 8 bits. This is also legal. And why? CS and code segment is not allowed any value to be loaded, right? For that matter, if I execute move DS, AX, it is alright. So all segments except the code segment CS are allowed in this instruction, but CS is not allowed. So this instruction is not allowed. So example of immediate addressing using the move instruction, right? So immediate value is loaded into a register, right? Constant value is loaded into a certain destination register. Now we look at direct data addressing mode, and direct data addressing mode specifies the offset address of the operand as part of the instruction. Examples are move AL, data. Over here, the contents of the memory location named data or the variable data would be moved into the AL register. And then this example, contents of the location whose offset address is 1234H would be loaded into the AL register. Now let's look at this example of this figure that is shown in this, right? Now 1234H, the contents of the 1234H would be loaded into the AL register. Now since it is an 8-bit register, only one memory would be referenced. Now how the memory address would be calculated? DS is 1000H. So we will first execute DS into 10H, which would come out to be 10,000. Then we add the offset, which is 1234, 1, 2, 3 and 4. So what is the 20-bit physical address? 1, 1, 2, 3, 4 hex. Right? So this address is the source and the AL is the destination register. So this memory location would be accessed, and whatever value is stored in this memory location or the contents of the memory location, in this example it is 8A. So this 8A value would be moved into the AL register. So AL would contain a value of 8AH after this instruction has executed. Now as you can see that whenever the processor reads this instruction completely, right, the processor gets a value 1234H, right? But now 1234H is not the data, it is address of the data. So processor has to make one memory reference in order to get the data, which is 8AH. So this addressing mode is slower as compared to the register addressing mode and the immediate data addressing mode. Now some examples of direct data addressing mode. Move AL, number, right? We assume that contents of number would be moved into the AL register. So what should be the size of the variable number? It should be 8 bits, right? And of course, since AX value is moved into X, the variable cow should be 16 bits, and so on and so forth, right? This is an interesting example. Sorry. So in this particular example, right, we are addressing a offset of 2000H, but the segment register is now ES, and the contents of AL would be moved into this particular location. Now, how would we calculate the address? Address would be calculated by ES into 10H. Plus the offset, which is 2000H. Now, register indirect addressing mode. It specifies the offset address of the operand in either BX register, BP, SI or DI. So in register indirect addressing mode, we always refer to it by the brackets, square brackets. So this is a proof or sign of register indirect addressing mode, right? So only BX, BP, SI and DI can be used in brackets. So let's look at an example. BX is 1000H and DS is equal to 0100H, right? So in this instruction, contents of 16-bit contents of this location would be moved into AX, right? So for 16 bits, it means 2 addresses would be generated. So what would be the physical address of the first location? DS into 10H plus 1000H. So DS into 10H basically is 1000H plus 1000H, it would be 2000H, right? So 0200H, contents of this location, and contents of 02001H would be moved into this register, right? So it's you following little endian, contents of this memory location would be moved into the AL register, and contents of the next higher location would be moved into the AH register. Now please solve this. You have to write the addresses and the contents of memory. So this is the answer, right? Basically AX was 1020H, so this was AH and this was AL. So contents of AL, which is 20H, would be placed in the first location, which is 0400H. The 20 is placed, which is the low byte, placed in this address, followed by the high byte at the next address, and high byte is 10. So high byte is stored in the next location, which is 04001H. Some examples of register indirect addressing mode, they are very straightforward, so please read those and go through with this. Now we look at register relative addressing mode, and in register relative addressing mode, we have in brackets either BX, BP, SI and DI plus or minus a constant displacement, right? So what is an example? Example is move in brackets BX plus 10, and you should assume that if 10 is written, it means 10H. So this is basically, so now how it would work? Contents of AL would be moved into DS into 10H plus BX plus 10, and contents of AH would be moved into DS into 10H plus BX plus 10H plus 1H, right? So as we know previously, this would be computed first and the result would be added into DS into 10H. Similarly, this would be computed first and the result would be added into DS into 10H. So please carry this exercise out and let me know about the memory map. This is the answer, right? Please verify. Now this is a very good exercise. I would invite all the students to please carry out this exercise and let me know about the answers or the results. Now let's look at base plus index addressing mode. And in base plus index addressing mode, as the name says, we'll have a base register which can either be BX or BP. These are the two base registers, right? It can either be BX or BP, followed by an index register which might be SI or DI, source index or destination index. So examples would be move BX plus DI in brackets comma CL, right? The contents of CL are moved to this particular single address is generated, right? DS into 10H plus BX plus DI. Again, BX plus DI would be calculated first, and the 16-bit result would be added into DS into 10H. Similar is the case for other examples. Now, if BP is used in the brackets, then the segment that is used is the stack segment. That is the main point. So for BX, use the data segment, and for BP, use the stack segment in order to generate the addresses. Now base relative plus index, right? So as we know that we'll have a base register, we'll have an index register in the brackets, and we'll have a constant relative value in the bracket. So examples are straightforward. Move AH comma BP plus DI plus 3, base plus index plus relative. Move AX comma file BX plus DI, right? So this BX is used, so segment register in this example would be used as DS into 10H, and plus BX plus DI, BX plus DI. So this would be calculated first again, and the result would be added into DS into 10H. What about this? How the offset would be calculated now? Since BP is used, stack segment would be used in this example, SS into 10H. And of course we'll have the offset would be calculated by using BP plus SI plus 4. So again, like always, this value would be calculated first, and the 16-bit result would be added into SS into 10H. Now after the data addressing modes, we can take a look at the program memory addressing modes, and they are used with the jump and the call instructions. So jump and call instructions basically use the program memory addressing modes, right? So what is the evidence that you are using program memory addressing mode? The address or evidence would be that you would be using an opcode of jump, or you would be using an opcode of call. So program memory addressing modes are again of three types: direct program memory addressing mode, relative, and indirect program memory addressing mode. Now these addressing modes would be dealing not with the data but with the program execution. So then hence they are termed as program memory addressing modes. Similarly, stack memory addressing modes would access the stack. So whenever we are using the stack, we would be using the stack memory addressing modes. And again, we can use the famous push instruction and the pop instruction. Push adds data on the stack, and pop adds data, removes data from the stack. Similarly, the call instruction, like I discussed in my previous examples, the call instruction would push the return address on the stack, and the pop instruction would pop the return address from the stack. So we'll look at these addressing modes later on. Right. So we can now look at some examples, right, of code evaluations. We can try to write an assembly language code to evaluate 2a plus b, where a and b are 8-bit variables, right? So as a sample answer, we can see that we can XOR AX comma AX, which would always clear the X. Then we move an A into AL, which is the variable A, and then we move a 2 into BL. Then we execute mul BL, and mul BL instruction multiplies the contents of AL and BL. AL is multiplied by BL, which results in a 16-bit value being stored in the AX register. Right. Now then we add the value of B. Right. So over here we have evaluated 2A. Now we have to evaluate plus B. So B is added into this by this instruction. So AX contains 2A plus B.